Good morning. So we were talking last time about how to project a moment on an axis. For example, here in this figure, you have axis AA prime and BB prime, for example. If you are interested to find the moment of vector F, of force F about axis AA prime, what you should do is first you consider any point on axis AA prime, for example, point O. And then you do first the moment of vector force F about O, which is OA vectorial F. And then in order to, this will give you a vector moment, which is a moment about point O having three components, which are moment about x-axis passing by O, y-axis passing by O, and z-axis passing by O. Now, if you are interested in finding the moment along axis AA prime, which is passing by point O, you should do the projection of the moment vector on the AA prime axis. And you know that to do a projection of a vector on a line, what we do is we do dot product the vector, dot product unit vector of the axis. So this is called the triple scalar product. UA dot R vectorial F, which will give us directly the projection moment of a vector F about a certain axis. Now, you can do it in steps. You can first calculate the value of R vectorial F, and after this, after you find this vector, you do dot product UA. But you have another calculation method that is faster. What you can do, it's like the matrix method. You place your three vectors in a matrix. The first line will be the components of the unit vector along x, unit vector along y, unit vector along z components. The second line will be the components of the position vector, Rx, Ry, Rz. And the third line will be the components of the force vector, Fx, Fy, F. And then, as we did in the calculation of vectorial product, it's a plus above the x component of the unit vector, minus above the y component, and plus above z component. And then, to start with calculation, you put plus UAX times, we drop the column and line of UAX. The remaining numbers are these four, so I do plus RY FZ minus FYRZ times UAX. Then I move to minus UAY. Minus UAY, I drop the column and line of UAY. So it's minus UAY times RXFZ minus FXRZ. And then finally, I do plus UAZ times RXFY minus FXRY. And in this way, I obtain the component of projection of the moment vector. Now, in case you want, if you remember, we said this is the projection component. Okay? So this will give me a number. This calculation will give me a number, which is the projection component. It can be positive or negative. If the projection is along unit vector, it will be plus. If it's opposite, it will be minus. And then, if I want the projection vector, I then multiply my component by the unit vector. So if I multiply the result by the unit vector, then I get the projection vector. Projection vector. Any question on this? So now we will do an example to do practice on how to find the moment about a certain axis. The rod shown below is supported by two brackets at A and B. Given that the magnitude of F is 700 Newton, find the moment about axis AB due to F. So whenever they ask me to find the moment of a force about an axis, okay, the first step I do, I select a point on the axis. So here my axis is AB, I can take point A or I can take point B. So I will take the point with the simplest coordinates. You can see that A is the origin of my frame, so it's easier to work with A since the coordinates of A are, so for A it's 0, 0, 0. And for B, the coordinates are along x 0.4, along y 0.2, and 0 along z. So 0.4, 0.2, and 0. And for point C, I have C in plane xz. So I have 0.6 along x, 0 along y, and 0.3 along z. Okay. Now, to start with, we said that we will choose point A along AB. Okay. So we have to do the moment of F about A. But instead of doing several steps, first finding the moment of A, then projecting, we can say from the beginning that we can calculate the triple scalar product. Okay. So what I should find is the following. Since I want to project on AB, so I should do unit vector of AB dot product R vectorial F. What is R here, the position vector? I want to find the moment of F about A. So which vector I should consider? I can consider, I have two
RAV.
options. I have two options. F is passing by C. The line of action of F is passing by C and it's passing by D. So I can take or AC vectorial F, or also I can take a D vectorial F. Which point is easier? Working with D is easier because D has only one component along Y. So I can do AD is, point D has as coordinates 0, 0.2, 0. Okay? So here you have the freedom to select what you want. You can do or AC vectorial F or AD vectorial. So if we choose to do AD vectorial F, okay, then how will be our matrix? For our matrix, the first line will be the components of the unit vector of AB. So the first step to do here is to find the coordinates of unit vector AB. And already I have coordinates of A and B, so I can apply to find UAB. So UAB vector is equal to, I have 0.4i plus 0.2j
Okay.
over, yes,
Just a question. You have explained it in the last session, but what makes R of AD equals to R of A?
R of AC you mean?
No, R of AD equals
R
AC.
of
I
AD.
don't know. Yani, two R. What makes them equal in the formula?
Sorry, I didn't understand the question. Can you please repeat?
Yes, you said in the last
Yeah.
time that we can take any point
Yes.
in order to calculate R.
The moment.
Yes, can you
Yeah.
just explain why? No?
Why we can take any point?
Yes,
Okay. Yeah, I will explain it back to you. Just 1 minute, okay? So over radical 0.4 square plus 0.2 square. Look, why we can take any point? Because if you go back to the definition, if I have a point here, okay, this is point A, and I have a force F. Let's say this is force F, okay? This is F. Now, if you consider the line of action of F, so even for example, this is point B, let's say, okay, this is the point of application of F. Why you can take any point on the line of action? Because look, if I take any point here, okay? When you do R vectorial F, by definition, let's say you consider this vector position R, okay? So if you do AC vectorial F, or you do, for example, if I take another point here, from the other side, I will take it now. If I take a point here, for example, so this is C and this is D, okay? If you do AC vectorial F, by definition, when you do the vectorial product, okay, it is in magnitude equal to what? It is equal to magnitude of AC times magnitude of F times sine of what? Sine of angle in between, okay? Let's say when I consider AC and F, what is the angle in between? It is this angle, okay? When you say F times AC sine theta, what is AC sine theta geometrically?
The perpendicular distance
Yes,
between the
exactly.
point.
It's the perpendicular from A to the line of action of the force. Okay? So it is this distance D. And always R sine the angle will give you D, whatever is the angle. Because now if you take another point, the point here, point D, you will have a new angle alpha. So here I will have a new angle alpha. Okay? And my result will be FAD sine alpha. Okay, but what is AD sine alpha?
The same, the perpendicular distance.
Exactly. This is why you can take any point on the line of action of the force. This will not affect your result.
Yes, so excuse me, doctor, here we took AD.
Yes, you can take AD, you can take AC as you like. Both will give you, if you try it,
Yes,
if you do the vectorial product, both will give you the same result for the moment.
okay. Thank you, doctor, so much.
Well, okay. So we found the components of unit vector of AB. And for vector AD, we have already the coordinates of point D. So AD vector is equal to 0.2 along J. And we still need vector F. For vector F, how to find vector F? Vector F
Magnitude
is the
and unit vector.
magnitude. Okay, they gave us the magnitude. And since we know that it's passing by 2 points, C and D, and it's directed from C towards D, then it is times unit vector of CD. Okay, so now what we still need to find is unit vector of CD. To find unit vector of CD, as usual, we do x of D minus x of C, so it's minus 0.6i, y of D minus y of C, so it is plus 0.2j, and 0 minus 0.3, so minus 0.3, and over radical of 0.6 square plus 0.2 square plus 0.3 square. Okay, and now let us see how we can do the calculation in the matrix form. So as you can see here, they followed the same steps. First, we find the coordinates of all points. Then, here, instead of choosing AD, they selected AC. So it's also right. Okay. So they selected vector AC. So they found our AC vector. We have, as we did for F, it's F unit vector CD. We can get the components of F. And they found the components of unit vector of AB. And now the third step is to calculate the matrix. Okay, so in the first line we always put the components of the unit vector on of the axis on which we want to project, which is AB. So as you can see here, I will take the coordinates of AB vector. I have along I 0.9894, along J 0.447, and no component along K, so 0. Then for vector AC, I put the components at 0.6 along I, so I start by 0.6, no component along J, so 0, and 0.3 along K, so I put 0.3. And finally, for vector F, I have along I minus 600, along J 200, and along K minus 300. So here it's a typing error, it says 3. Okay, and now next step to do is to do the calculation. Okay, so as we said, what we do is we put a plus above the UABX, minus above UABY, and plus above UABZ. And now we start plus 0.894 times. The remaining numbers will be 0 times minus 300 minus 200 times 0.3. I get my first component. Okay? And here, no IJK, it's a number. So I should add numbers together. So now minus 0.447 times 0.6 times minus 300 minus 600 times 0.3. So I obtain the component along the second component. And for the third component, it is plus 0. So it's 0 times something. So it's 0. And now when I do the calculation, I get that MAB is minus 53.64 Newton meters. The minus sign will indicate that the vector, the moment of F about AB is directed from what to what? From which point to which point? From A towards B or from B towards A?
B towards A.
B towards A. Because when I projected on AB, I got a negative result. So my projection will be directed from B towards A. Okay? And now, if you want to find the projection, so this is the projection component. This is the projection component. If you want to find the projected vector, okay? So now, for the projection vector, how can I find it? What should I do?
We add UAB.
Yes, exactly. So we say that a MAB vector is equal to MAB projection times unit vector of AB. So it's equal here to minus 53.64 times, I just replace the unit vector components, so times 0.894 along I and plus 0.447 along J. I can do the expansion and find the IJ components of this vector. Any question on this problem? Okay. So let us start something else. Okay, so now, until now we have defined how to calculate the moment of a force in 2 dimensions and in 3 dimensions. So now we will learn how to calculate the moment of a couple. Okay, and what is a couple? A couple is defined as 2 parallel forces which have the same magnitude, opposite directions, and which are separated by a perpendicular distance d. So this is how we define a couple. It is created by 2 forces that are equal in magnitude, having same direction but opposite sense, if you want. Sometimes for sense and direction we confuse them. In general, direction we don't consider just the parallel line of actions. When we talk about if it is up or down or right or left, we talk about the sense. So here I have opposite sense and same. They are parallel, same. We can say same direction or same or parallel line of action. okay, but opposite in sense. So here, any two forces that satisfy these conditions can create a couple, okay? And we will see that a couple is a free moment vector. What do we mean by free moment vector? So if I calculate the moment about any point in the space of this couple, it will be the same. So let us demonstrate why. Because look, consider you have two opposing forces, plus F and minus F. A is a point on minus F here, and B is a point on F. So this is A here, and this is B. And I want to calculate the moment of this couple about any point. So I will take an arbitrary point in this space. I will name it O. And I will try to find the expression of the moment of the two forces, which is the couple of forces about point O. So, as usual, to calculate the moment about a point, I consider vector position from O towards any point of the force. So first, for vector plus F, the moment is OB vectorial plus F. And for minus F, I have OA vectorial minus F. So now if I do the addition, I should add RA vectorial minus F plus RB vectorial F. And you know that from characteristics of vectorial product, I have in common between the two vectorial F. So I can, if I respect the order, I can take vectorial F into factor. So I have RB minus RA vectorial F. And what is RB minus RA? Vector RB, as you can see here, is vector OB. And vector RA is vector OA. So I end up with M equal to, so vector M is equal to OB vector minus OA vector vectorial F. And I know what is OB minus OA. It's OB plus AO, okay? And OB plus AO is AB. You know this characteristics of vectors addition, okay? So it is equal to OB plus AO, okay? Okay, so when I add two vectors like this will give me, so of course, vectorial F. So this will give me AB, because AO plus OB, okay, is AB vector. So it's AB vector vectorial F. So what can I deduce? AB vector vectorial F vector. What can I
That
deduce from this?
that
Yes.
that the moment of the couple is equal to the distance, the perpendicular distance between the forces multiplied by the force.
Look, here A and B can be any 2 points of F. مش ضروري يكونوا على perpendicular, but you will see that when you do AB vectorial F, you will AB sine angle, sine theta will give you the distance D you are talking about. Okay, so here you can deduce that the couple moment is independent of the point. So this is why we say
Yes.
it's a free vector. It's independent of O. It's only depending on the force F and the distance between the forces. So here, if I take A here, for example, so if this is A and this is B here, okay? So when I do AB vectorial F, so this is AB vectorial F, okay? This is point A on minus F, and this is point B. By definition, when I do the vectorial product, it's AB times F times sine theta, okay? And theta is the angle between AB and F, okay? And this angle, when I do AB sine theta, what do I get? I get the projected distance.
Yes.
Okay? So I can deduce here that the magnitude of R vectorial F is F times AB times sine theta. And I replace AB sine theta by D. So in magnitude, it's F times the distance between the two forces, the perpendicular distance between them. Okay? Any question on this? So now, we will see together that for the couples, we can have forces of different properties, different magnitudes, and producing same couples. We'll see how. So now here, just for application, if you want to find here the moment of this couple about O, no need to do sum of moments about O. I can directly say that the moment vector is a free vector, so I can take any point on F, any point on minus F, and say that the moment created by this couple is. So here you can do two things. If you started from B, if you go from B to A, you do BA vectorial what? Vectorial F. And if you select to start from A, so if you do AB, you do AB vectorial minus F. And of course, it's the same result, okay, because you have the two are opposing vectors. So, or always, when I start from a point and I end by the other, I do vectorial the force passing by the second point. So BA vectorial F or AB vectorial minus F. Okay. Now, they selected to do BA vectorial F. So if I do BA vectorial F, I have the coordinates of B and A, so I can find vector AB. Okay. Vector AB will be 3 minus, so here they considered vector BA. So vector BA, okay, will be 4 minus 3 along I, and minus 1 minus 2 along J, so plus I minus 3J. And vector F is given, it's I plus 3J. So here, to do the vectorial product, I can do the matrix form. So it's IJK in the first line. The second line components of vector BA, which are 1 minus 3, 0. And third line components of F vector, which is 1, 3, 0. And now I do the vectorial product. Okay. Can you tell me why I can expect here that along I and J, I will have a component 0 of the couple?
Because they are passing through the axis.
Exactly, because the two forces are in which plane? The two forces are in plane XY. So they cannot produce moments about X and Y because or they are parallel to them or they pass by, they intersect them. So they cannot create a moment about this axis. So always, when you have forces in a plane, they cannot produce moments about axis of the plane. So here, they will only produce a moment about the axis perpendicular to the plane, which is the axis. So you can directly here put 0i, 0j, and you can verify this from calculation. And finally, to find the component along k, it's plus k times 1 times 3 minus 1 times minus 3. It will give you the component of your moment along K. Any question on this? Okay. Now, as I told you, equivalent couples means that they produce the same moment. But we can obtain equivalent couples with completely different forces in direction, in magnitude. Let us see how. So in this example, you can see this. In this example, you have first, for example, you have forces like this, two forces in xz plane. Okay, so this is x, This is Z, and this is Y. You have that the two forces are of magnitude 20 Newton. So 20 Newton and 20 Newton. And the separating distance between them is 150. So in total, the couple will be in magnitude 150 times 20, which is 3000. If the dimension here are in millimeter. If you keep the dimension in millimeter, you obtain that the couple is 3000 Newton millimeter. Okay? Or if you want to convert to meter, it's 3 Newton meter. Okay? Now we will see that completely different forces will give us the same moment. Same moment in direction, in sense, and in magnitude. Here the moment is along vertical axis 1. We'll take other combination of forces. So now, instead of choosing our forces in Z, they choose forces in X. So I have two forces in X direction, and both have a magnitude of 30 Newton, and they are opposite, so they create a couple. So here I have 30 Newton and 30 Newton. And the distance in between is 100 millimeter. So here, this distance is 100 millimeter. And now if you calculate the corresponding couple, first as magnitude, it is 30 times 100. So it will give you same result, 3 Newton meter. And what about direction and sense? What to do to determine the direction and sense of the moment? We use the right hand rule. Okay? So how to use your right hand rule here? You take your right hand, you put your 4 fingers along the first force and the face of your hand looking towards the second. And you curl your fingers. When you curl your fingers from this force towards the other, try to do it with your right hand. Your thumb will point upward. Okay? And here also try to do it. Take your right hand, put your 4 fingers along this force, and your face, the face of your hand looking at the second force, and curl your hand. Also your thumb will point up. Okay? So here I have completely different conditions, different magnitude of forces, different direction of forces, different distance between the forces, but in total, when I did the couple, I obtained the same couple. So to say that I have equivalent couples, the two couples should produce the same moment vector. This will make them equivalent. Now, also, I can change the plane of forces and still obtain the same couple. So here, if you have the 30 Newton forces here, instead of being in the plane down, they can be here. Okay, and still they will create the same couple. So this is the thing illustrated here. I put 30 Newton forces, but on a parallel plane on the upper face. I will still obtain the same couple. So if I do the right hand rule also, it's producing a moment like this. So I turn my hand like this, my thumb will point upward. So this will give me the direction and sense of M, vertical upward. And in magnitude, it's also 30 times 100. So here, all these couples are equivalent because they result in the same moment vector. Any question on this? Now, how to calculate the resultant moment of couples? So if I have several couples acting on a body, all I have to do is to do the summation. Okay? So since moment couples are free vectors, they can be added vectorially. So all I have to do is to add all vectors. I get the total resulting moment. Now, let us consider an example, a device called Aralamite is used to replace slipping motion with rolling motion. If the belt which wraps between the rollers is subjected to a tension of 15 Newton, determine the reactive forces N on the top and bottom plates on the rollers so that the resultant couple acting on the rollers is equal to 0. So what do we have here? What we have here, we have two rollers, okay, between two belts. I have normal reaction between the belts and the roller, but for this normal reaction, I don't know the magnitude. I want to find the magnitude in a way that the resulting couple acting on the roller is 0. So here I have two couples acting on the rollers. I have the couple of N forces, which is the reaction between the belt and the rollers. So for this couple, if I want to find it, I should look at the distance between the two forces. So this is the line of action of the first force. This is the line of action of the second. I need to determine the perpendicular distance between them. Okay? In order to find this distance, if I look well at my figure, I can easily find it. Why? Because they gave me here that this angle is 30 degrees. So I know this angle. And I know that the distance separating these 2 points here is equal to 2 times the radius of the roller, because it's from center to center. Okay, so this is from center to center. So it's equal to 2 times the radius. And since the radius is 25 millimeters, so the total distance separating centers is 50 millimeters. So now, what will be the perpendicular distance? All I have to do is 50 cosine 30 degrees, okay? Because the angle is given. So the perpendicular distance between them is 50 cosine 30. So now I can find the first
Doctor,
couple. Yes?
excuse me, isn't even the perpendicular distance to R or no?
No, it's not the perpendicular distance to R, because look, you have to be, for it to be perpendicular, you should have a right angle between the normal line and the line joining the center. But it's not a 90 degrees angle, this one. Okay? It's not 90. It's equal to 60 degrees, because here you have 30, okay? Here you have 90. So since the angle between this line and the normal line is not 90, you need to do the projection. You need to find the perpendicular. And to find the perpendicular, in this right triangle, you have the hypotenuse is 50 millimeter, and this angle, or this one, is 30. Okay, so all you have to do is to find the distance D is to do 50 cosine 30. Okay?
Yes, thank you.
Okay. So I will open a new session to continue.